Hello, today we are going to talk about the effects of the atmosphere on optical observations. Specifically, we are going to talk about seeing and turbulence. The atmosphere is not uniform. The atmospheric refraction effects are also not uniform. There are pockets of hot air and cold air of various sizes. They are distributed from hundreds of meters to few centimeter scales. And whenever there is a difference in temperature, it causes a difference in the refractive index. So, any light that is passing through will get phase distortions. Some parts of the wavefront will travel faster than others. So, if you have a plane wavefront coming from a point source at infinity, as it passes through the atmosphere, the wavefront is going to get distorted, and the distortions are going to change with time, because with wind movements these small pockets of hot and cold air are going to move very quickly. Now, you can see in this illustration that these wavefronts are changing slightly with time. Now, whenever the wavefront changes, the rays of light which are corresponding to these wavefronts, which are perpendicular to the local wavefronts, are going to move in different directions. What does that do? It causes movements in the positions and the shapes of stars. So, this is a slow motion image of a star taken from a telescope, and you can see that instead of appearing like a very sharp point like disc, you can see the pattern slowly change. There are two effects which we need to consider here. One is the overall motion of the star's position, or the tip tilt. You can see that there is a overall motion that occurs in this image, and there are small speckles which get distorted. There are speckles which become brighter and fainter, and they change with time. They do not necessarily repeat. And this is of course a very slow motion video. The actual speed of this change is very fast. It changes hundreds of times every second, depending on how quickly the wind is moving these pockets of air around. There is one important parameter that we need to talk about when we want to understand the effect of the atmosphere, that is the Freed parameter. Now, the Freed parameter is the length scale over which the wavefronts change significantly. Now, if you have a wavefront like this, your Freed parameter would be some scale where the wavefront does not change significantly. Now, for a good site, a good observing site with very clear smooth atmosphere, your Freed parameter, which is denoted by R0, will be large, up to 20 centimeters, 25 centimeters, which means that the wavefronts are smoother and more planar. They are not as distorted. For a poor site, R0 will be smaller. It can be as small as 5 centimeters, which means that the wavefronts are rougher and they change very quickly as you look in different directions. This obviously also changes with the zenith angle zeta and with wavelength. So, if you go further away from the zenith, you are looking through more and more atmosphere, so you encounter more turbulence and your Freed parameter will become smaller. So, as you get closer to the horizon, your seeing is going to get worse and your Freed parameter is going to become smaller. To be specific, R0 changes as cos zeta raised to the 3/5 power and lambda, the wavelength, raised to the 6/5 power. We will not talk about where these indices come from. They come from the Kolmogorov theory of turbulence, which we can talk about in a more advanced lecture. Now, let us look at what is called a Speckle pattern. What does the atmosphere do to an image? If you have a telescope and there is no atmosphere, if you have a circular aperture, the image looks quite sharp. It looks like a very sharp point, and the size of that point is given by standard diffraction theory, and it is about lambda by d, where lambda is the wavelength and d is the diameter of your telescope. Now, if you have the atmosphere, these are some images taken from Popovich et al. You get a lot of patterns you can see here. These are called speckles. These are different snapshots of the star taken through the atmosphere at slightly different times. You can see small bright spots. These are the speckles, and the individual speckles are the size of the airy disk. So, this is limited by the diameter of your telescope, but you have a huge spread of these speckles, and this spread decided by the Freed parameter, how large it, smaller the Freed parameter, larger the speckles. Now, when you take an observation of a star, you typically observe it for a long time, and each of these individual snapshots gets averaged out, and you get an average distribution of the speckles, and that is known as the seeing disk. So, the size of this seeing disk is given by lambda by R0, where R0 is the Freed parameter, and this is the size of the star you would see when you take an image through a telescope. Now, we can also look at what different ratios of telescopes would look like. On the vertical axis, you have different ratios of d by r naught. So, let us say d stays the same, but r naught decreases. As r naught decreases, your seeing becomes worse and worse, and you look at what the image looks like for different snapshots in time and what the average image would look like. If you had a r naught which is very large, let us say 20 centimeters, and your d was about 20 centimeters as well, you get some motion of the airy disk, but you will get a very sharp point. You have each individual snapshot looks like a airy disk, it moves a little bit, but the average image is still very sharp. As your Fried parameter becomes smaller and smaller, you get a lot more speckles which are distributed over a larger area, and your average size becomes larger and larger. So, what we can summarize is that if you have a small diameter telescope where your telescope diameter is smaller than the Fried parameter, your image size is limited by the size of the telescope itself, it is lambda by d, and this is nearly diffraction limited. So, when you look with your eye or with a small binocular, you will be diffraction limited if your r naught is fairly large. But if you go to a larger diameter telescope where d is larger than r naught, your image size is no longer limited by diffraction, it is limited by your seeing. So, your image size is lambda by r naught, and this is what we call a seeing limited observation. When turbulence is really strong, you can have yet another effect. The wavefronts can converge and diverge, causing the brightness to increase and decrease. You have more or less light coming into your telescope aperture, and this is most prominent for stars near the horizon. Here is a small movie of Sirius, the brightest star, going across, observed through a telescope, and you can see that the brightness is rapidly changing as well as the colors are changing. This is of course much less for planets, because planets are larger in size and different parts of the planets will twinkle differently, and the average effect is that the twinkling magnitude reduces. So, in summary, we have talked about turbulent effects of the atmosphere. The atmosphere has pockets of turbulent air which are colder and hotter, which have different refractive indices, and the changes in refractive index cause the incoming wavefronts to be non-planar. There are distorted wavefronts which come in, and the star's image changes rapidly, smoothing out the image. What you effectively get is the seeing disk depending on the conditions of the atmosphere, and with strong turbulence you can even get changes in brightness which change as a function of time and frequency.